Tonight, we're going on a gentle journey, a journey far beyond our planet, far beyond our sun, into the deep, calm darkness of space. We are going to visit something mysterious, something that, as far as we know, may not even exist, but that scientists can still imagine and study and dream about. Tonight, we are travelling to meet a white hole. To begin this journey, take a slow, easy breath in and gently let it out. You don't need to focus too hard. You don't need to remember every detail. You can simply let the story flow over you, like a soft, quiet river. Some of the ideas we will explore come from physics, from mathematics, from the minds of scientists who have spent their lives thinking about space and time. But tonight, you don't have to solve equations or understand every technical word. Just listen. Let the pictures form in your mind, softly and simply. We'll start with something you may already know: black holes. Because to understand a white hole, we first need to remember what a black hole is. Far away in space, a giant star lives out its life for millions or even billions of years. It burns with a fierce, steady glow, turning its fuel into light and warmth. But eventually, that fuel runs out. The star, once proud and bright, can no longer hold itself up against its own gravity. Gravity is the gentle force that makes you feel your weight on your bed, that keeps the moon circling Earth, that keeps Earth circling the sun. But for a very massive star, gravity can become overwhelming. When the star has no more fuel to burn, it begins to collapse, shrinking, falling inward, crushing itself into a smaller and smaller space. If the star was heavy enough, this collapse cannot be stopped. The star's matter falls inward until it becomes so dense and its gravity so strong that nothing, not even light, can escape. This is how a black hole is born. A black hole is like a cosmic trap. Anything that gets too close, anything that crosses a certain invisible border, is lost forever. This border has a name: the event horizon. You can imagine it like the edge of a waterfall. In a dark, far away from the waterfall, the water flows calmly. You could still swim away or steer your boat to safety. But as you get closer, the water flows faster and faster. Right at the edge, the current is so strong that even if you tried to paddle with all your strength, you cannot escape being pulled over the fall. That edge, that point of no return, is like the event horizon of a black hole. Inside the event horizon, gravity is so strong that every possible path leads inward. Nothing can climb back out, no matter how fast it tries to go. That's why black holes are black. No light can escape, so they appear as dark holes in space, surrounded sometimes by bright disks of hot gas and dust falling into them. Now, scientists use a set of rules to describe gravity and space and time. Those rules come from a theory created by Albert Einstein more than 100 years ago, called general relativity. General relativity says that space and time are not just empty nothingness. They can bend, they can stretch, they can curve around stars, around planets, and around black holes. A simple way to imagine this is to think of space and time as a flexible sheet, like a soft rubber blanket. If you place a heavy ball in the middle of the blanket dips down. If you then roll a smaller ball across the blanket, it will curve around the dip instead of moving in a straight line. In a similar way, the presence of mass and energy changes the shape of space and time. And that change in shape is what we feel as gravity. Black holes are places where space and time are curved in an extreme way. They're like deep wells in the fabric of the universe. When scientists use the equations of general relativity to describe a black hole, they discover something curious. They find that, in a certain simple form, the equations do not just describe a black hole in the present. They also allow a kind of mirror image, a time-reversed twin called a white hole. If a black hole is a place where things can go in but never come out, then a white hole is the opposite. A place where things can come out but nothing can ever go in. Where a black hole is like a cosmic drain, a white hole is like a cosmic fountain. Matter and light can be thrown outward, but never swallowed. Now imagine the opposite. Imagine a white hole. This time you begin your journey inside. You try to travel inward, toward the centre, but the paths all bend outward instead. If you start near the event horizon, you find that you are always being pushed away, thrown out into the wider universe. You can never cross into the white hole. You can never go inside. From your point of view, the event horizon is again a border, a point of no return. But this time, it's a border you cannot cross from outside to inside. You can only cross from inside to outside if you were somehow born within it. You might wonder, how can something like this exist? Where would the stuff that comes out of a white hole even come from? Why would the universe have objects that spit things out without ever taking anything in? These questions are part of the mystery. One way to think about a white hole is as the future outcome of a black hole's past. Imagine watching a movie of an object falling into a black hole. A spaceship gets too close. It circles, it spirals inward, and eventually it passes through the event horizon, lost forever. Now imagine you press a button and run the movie backwards. You would see a spaceship suddenly appearing near the black hole, racing outward, escaping into space. You would see matter flowing out from the black hole instead of falling in. This backwards movie is a kind of picture of a white hole. In a simple sense, a white hole is just a black hole viewed in reverse time. The equations of general relativity allow both possibilities, but our universe does not seem to treat time in exactly the same way in both directions. In our everyday lives, spilled milk does not jump back into the glass. A broken plate does not reassemble itself. Smoke from a candle does not gather itself back into a solid wick. These are things that happen one way in time, but not the other. We say that time has a direction. There is a past, and there is a future. Black holes fit very naturally into the way our universe behaves. Stars collapse. Things fall in. Disorder grows. White holes, with their strange, reversed behaviour, may not fit so easily into the reality we know. So far, we have spoken about black holes and their time-reversed twins. But there is something else hidden in the equations. Something that connects black holes and white holes in a very intriguing way. This is an idea called a wormhole. A wormhole is like a tunnel through space and time. Imagine that space is like the surface of a sheet of paper. If you want to go from one corner of the paper to the opposite corner, you could walk along the surface, travelling all the way across. But now imagine that you're allowed to fold the paper. You bring the two corners closer together until they touch. If there were a tiny tunnel Going from one corner to the other, you could step through it and arrive almost instantly without crossing the rest of the sheet. This tunnel is like a wormhole in some versions of Einstein's equations. A black hole can be connected to a white hole by such a tunnel. One end of the wormhole looks like a black hole. Things can go in, but not come out from that end. The other end looks like a white hole. Things can be pushed out, but nothing can enter. This particular structure is sometimes called an Einstein-Rosen bridge. In the pure mathematics, it is a smooth passage, a link between two regions of space-time. In science fiction stories, wormholes are often used as shortcuts through the universe. Spaceships pop into a wormhole near one star and appear near another star, across the galaxy, or even in another universe altogether. But in the realistic physics we understand today, such wormholes, if they exist at all, would be incredibly unstable. They would collapse almost as soon as they formed, closing the tunnel, trapping anything inside. Still, the image is beautiful. A black hole on one side, a white hole on the other, joined by a hidden road through the fabric of reality itself. Now let us drift for a moment through the silent darkness of space. Faraway stars shine like tiny lanterns. Some are red and cool, some are blue and hot, some are big, some are small. Planets circle them in slow and graceful orbits. Nebulas, clouds of dust and gas, glow in soft, colourful light, like cosmic clouds at sunset. In the distance, you can imagine a black hole, dark and quiet, surrounded by a ring of material, slowly spiralling inward, falling into its deep well. But somewhere else, in a place we are not sure is real, you can imagine a white hole. Perhaps it appears as a brilliant spot in the sky, a place from which matter and light seem to burst out as if from nowhere. If you tried to approach, you would find it difficult. The closer you get, the more strongly you are pushed away, as if the shape of space and time around the white hole refuses to let you in. From far away it might look like a bright, short-lived flare, a brief, intense explosion of energy that appears, shines, and then fades. Some scientists have wondered if certain mysterious events in our universe, such as gamma-ray bursts, extremely powerful flashes of light seen from distant galaxies, could be related in some way to white holes. This is still a guess, not a confirmed fact, but it shows how white holes give scientists a kind of playground for their imaginations, a way to test ideas about how space and time behave under the most extreme conditions. Even if white holes do not exist as isolated objects in our universe, the idea of them helps us to see how flexible the laws of physics can be. When physicists write down their equations, they do not always tell the universe what must happen. Sometimes they simply describe what is allowed to happen. Among all the possible solutions of those equations, nature then chooses which ones actually occur. Black holes are one type of allowed solution, and we have strong evidence. They are real. We've seen stars orbiting something invisible, moving so fast that only a black hole could be pulling them. We have watched hot gas spiraling into something that emits no light of its own. We have even seen the shadow of a black hole in a distant galaxy, using a network of telescopes spread across Earth, working together like one enormous eye. But white holes so far have not shown themselves. Yet even as a theoretical possibility, they are valuable. They push scientists to ask better questions. They encourage new ideas about the flow of time, about the beginning of the universe, about what happens to information that falls into black holes, and whether something might someday emerge again. Some researchers have gone even further with their imaginations. They have asked, could our whole universe have started as the inside of a white hole? Could the Big Bang, the event that began the expansion of our universe, be like matter and energy, emerging from a gigantic white hole in some larger reality? In this picture, what we call the universe would be the inside of a growing bubble, an expanding space-time, born from a kind of cosmic eruption. Outside that bubble might be a wider, perhaps calmer, perhaps older reality. We don't know if this is true. Right now, it is more of a poetic idea than a proven theory, but it shows how white holes, even as hypothetical objects, can help us imagine new ways the universe might be structured. And imagination is often the first step toward new discoveries. There is another question that white holes bring to mind. When something falls into a black hole, what happens to the information about what it was? Imagine you throw a book into a black hole. The book's pages, its words, its pictures, its meaning. All of that information seems to be lost forever. In ordinary situations, information is hard to destroy. You can burn the book and its pages turn to smoke and ash. But in principle, if you knew the positions of every molecule in the smoke and every speck in the ash, you might reconstruct what the book once was. In a black hole, this seems impossible. For a long time, this bothered physicists deeply. They called it the black hole information paradox. One idea, still being explored, is that the information is not truly lost, that it may somehow be stored on the surface of the black hole's event horizon, in a kind of super dense record. Another playful thought is that perhaps in some far future, what goes into black holes might emerge again through something like a white hole process, releasing stored information back into the universe. This is not yet a settled answer, but white holes give scientists an extra piece on the board, a new shape in the puzzle. Now let us return once more to the gentle image of space. You are floating in the quiet darkness, far from Earth, far from noise, far from worry. Around you, galaxies drift by, like glowing islands, in a dark sea. Each galaxy contains billions of stars, and around many of those stars are planets, some rocky, some gaseous, some icy and distant. Some planets might have oceans, and winds, and clouds, and perhaps even life. Scattered among these galaxies are black holes, silent, invisible, yet powerful. At the centre of many galaxies, including our own, there is a supermassive black hole, millions or even billions of times more massive than our sun. Gas swirls around them, stars orbit them. They help shape the life and evolution of their host galaxies. And somewhere in your imagination, there may be white holes too. Maybe they are rare, maybe they are short-lived, maybe they are only allowed in the math, but not chosen by our universe. Yet in your mind's eye, you can let one appear, a bright, sudden opening from which streams of light and particles emerge. They come out just once, in a rush, like air from a bursting bubble, and then they are gone. The white hole fades, leaving behind a quiet patch of space, slowly filling with stars and galaxies over billions of years. You might ask yourself, why do we spend time thinking about things that may not even be real? The answer lies in the way science works. Science is not only about what we can see directly, it is also about exploring the rules of nature to their limits. When we push those rules as far as they will go, we sometimes discover unexpected possibilities. Some of those possibilities will turn out not to exist in our actual universe. But others might reveal new truths about how reality behaves. In the past, black holes themselves were once thought by many to be just strange solutions to Einstein's equations with no real existence. They seemed too exotic, too extreme, and yet, over time, evidence piled up, until now we are quite sure that black holes are real, common, and important. So when we think about white holes, we are continuing that tradition of curiosity. We are asking, what else might be possible? How far does physics go? What happens when we flip time around or connect two regions of space with a tunnel? Or imagine our universe as just one part of something larger. Not every question will lead to a discovery, but asking them is part of what makes us human. As you rest here, listening to the story of white holes, you are sharing, in a small way, in that great human adventure. You are letting your mind stretch beyond the everyday, beyond streets and buildings, beyond jobs and schedules, beyond the familiar blue sky of daytime Earth, out into a universe so large that even our best telescopes can see only a fraction of it. In that vastness, there is room for many possibilities. Stars are born from swirling clouds of gas, live their brilliant lives, and then die, sometimes gently, sometimes violently. Black holes form from the ashes of these deaths, curving space and time into deep wells. And perhaps somewhere in a grand imagination of physics, white holes stand as their bright, elusive twins, always pushing outward, never taking in, like cosmic exhalations, balancing cosmic inhalations. We do not yet know if our universe truly breathes in this way, but it is peaceful to imagine. Now, return your attention gently to your own body, resting wherever you are. Feel the weight of your head, your shoulders, your arms, and your legs, supported fully by the surface beneath you. Outside, planets continue their orbits, stars continue to shine, galaxies continue to drift, and the great mystery of space and time unfolds patiently, quietly, over billions of years. Like starlight at dawn, space grows quiet, time flows gently, and you, carried by the calm current of your own breathing, are free to drift into deep, restful sleep.